All right, so just continuing on, if you're doing intersections, you got to think about making things equal, right? Like, what things do I make equal as Chavi so that I actually find where these two objects intersect? It's like a function with another function. Like how if you find the points of intersection of these two functions, what you do is you just set them equal and find roots, right? Like you're trying to find roots like this. It's exactly the same logic, but you have more than one variables to play with. So more than one variables need to be set equal to each other since you are in 3D, as you can see. Okay, so how do I do this? Well, one of the lines says that x1, x2, and x3 are equal to the following. They've given you here pretty much the parametric equations. Look, 2 plus t, watch here how I'm doing this. 2 plus t, right? 2 plus t is the first component. Can you see it again how we combine these? And this is your x1. Similarly, your x2 is exactly this. So just negative t. And then the third one, again, like this. 1 plus 2t. There you go. Read off the other guy at the same time in the same way. He says that his equation, this is called the parametric equation now that I'm writing down. The form that I'm writing it down is the parametric way. So he says that we have here 3 plus 2s, as you can see. The other one is the yellow one here, 2 plus s. And the last one is, of course, 1 plus 2s. Boom. All right. Would you ever imagine that I'm going to set components equal to each other? No way, right? Why would I ever do that? Well, obviously I'm going to do that. It's an intersection problem, right? So that's line 2, that's line 1. So what I'm going to do is set coordinates equal for intersection. All right, so let's start with the maybe with the x1s. So I go over here, 2 plus t is 3 plus 2s. The other one says minus t is equal to 2 plus s. And the third one says 1 plus 2t is equal to 1 plus 2s. If you notice that third one, by the way, notice that third one, it tells you that t is equal to s right there. Interesting. What about the others? Let's see what we get for the other ones over here. So, do they work if I actually substitute this in here? And do I get the same answer if I solve for t and s from these two equations? All three of them have to work with whatever I claim for t and s. I have to find what t and s actually is, by the way. Okay? I have to actually figure it out. So, let's check it out. Actually, I only need one. I lied. I only need one of the two. I only need either t or s for that intersection. And once I find what t or s are, if I find what t is, for example, I'll plug it here, do this addition, and I'll get the point of intersection. If I find what s is, I would plug it in here, do the addition, get the same point of intersection. It doesn't matter which one you do. Again, people get confused by this because of this freedom. It doesn't matter which one you find. All right. Looks like t is equal to 1 plus 2s over here. And t here is equal to minus 2 minus s. Well, I'm going to crash these. Okay. I'm going to get myself 1 plus 2s is equal to minus 2 minus s. Here I come. Combine them, you get 3s. Combine these, you get negative 3s. S is negative 1, therefore. So this is equation 1. just so we know what we're doing. This is equation 2, 3, and 4. Again, ignore this part over here on the right. So I better get right now, if I plug this here or there, I better get that t is -1. If I don't, I violate this one, and therefore there is no intersection. I think I should make this clear on the recording. So if I plug back this into any of 1 or 2, and I don't get t equals -1 from them, then I violated the third one that I need to satisfy, and there is no intersection. So even though there are solutions for T and S, if they don't satisfy this guy, no good. All three need to be satisfied, not just the first two. Let's see. I'm going to go ahead and choose to put it into 1. Doesn't matter which one you do, of course. So let's see what I get. T is 1 plus 2 times -1. Would you know it? I get that T is equal to -1. See? As desired. All right. So these are in agreement. So once you find that they're in agreement, point of intersection is given by A, plugging T equals -1 to line 1, or B, plugging S equals -1 to line 2, like I told you. Either one you do. But that's after I've checked that everything is cool. Here you go. So we put this then in. I don't know, I like the first one for some reason. We put this in. So if we put it in the first one, let's see what we would get. I'll just write it here and then copy it. 2, 0, and 1 plus -1 for the t, 1, -1, and 2. Perfect. So I'm just plugging in the t value right here. Nothing crazy. All right, so I'm doing A here. Bada bing, bada boom. And we get, what's 2 minus 1 there is 1. 0 plus 1 is 1. 1 minus 2 is -1. That's the point of intersection. There you go. Does this make sense, how I solved it? Find the parametric equations. Set each component equal to the other guy's component. You get 3 equations with 2 unknowns. The third equation acts as a proof that you're actually, good. You use the first 2 to find T or S, or both, and see if the third one is satisfied. If it is, you use the value either of T on the first line or S on the second line and get the point of intersect. How is that? And so you say here, just in case we don't have the equations in the form of parametric, do we just convert them? Yes. Yes, but some other times, guess what? If you had them, for example, in the scalar equation form, it would be a lot easier actually, because you would have something that looks like this. Y equals 3x plus 1 and y equals 2x. If you had them in scalar form, you would return back to doing things like you did in, functions. In general, though, it's parametric that we do this exercise in, for planes and for lines. If you have it in vector form, you can easily read the parametric equation out of it. If you have it in scalar form, it's much easier to actually solve. You solve it the way you're familiar with. Should I move on to this one? If we have time. All right, I think that was for that. So for the plane, in the line, it's a little trickier, but again, you can write their equations in parametric form and then try to intersect them. You will see, though, I think we should really leave this one for next time because I see the time, but I will say something here about it, okay? I wanna prep you a little bit. So a line and a plane, let's see a little bit, George, on Discord here to understand what kind of scenarios we could face. Okay, let's see George a little bit. Can't I show myself a little bit larger? There we go. So, okay, here's a line. Sorry, a plane. And I'm going to pick up a pencil for a line right now. Here. What's one scenario here? How could they intersect? One scenario. What do you think? One of the scenarios would be what? To intersect at a what? When you say 90, like you mean the degrees, but I was looking more for a point, a line, another plane. Like what kind of thing do you have if you see this, you know? Like what would if I scratched a little bit here, the plane, you would see what on it? Point. Great. So that's one scenario. What about this scenario? How do they intersect in this scenario? Ah, okay. And then there's another scenario, which is this one. So what about now? What's the description of the intersection? Is it a point? What is it? What do you think? Line. Yes. So you have intersections possible that are a point, nothing, or a line. How do I figure it out? Well, the one that's like this is fairly easy to figure out because I'll tell you. You can look at the vectors that we have, and if this guy is a scalar multiple of these guys, okay? So for example, going back to me, let's say there's vectors here, okay? Like there's a vector that points forward like this. If my line also points forward, then this vector on the plane can describe it. You see? So if we find that one of the direction vectors right now is parallel with our line, we don't have an intersection. Well, wait a minute. I lied. If we find that one of the direction vectors is parallel, okay, we have to also check if the line is on the plane or not, because we could have this scenario or this scenario right now. So we have to check to see if one point that belongs on the plane does not or does belong on the pencil. If a point on the plane also belongs on the pencil while this is happening, it means they look like this. If a point on the plane doesn't belong on the pencil while the previous is true, they look like this. So those tests, right, would tell you if you have a line of intersections, like a line intersection, or no intersection. But like we said, you could also have this kind of thing. So to see again all of that, right, I'd have to go back here. I have to check what's going on with these, if any of these are parallel, right? Let me make sure I cover all of the situations here. So back on my camera 1 sec before we close. Okay, so again, let's say I have a direction vector toward your face and one that's going up, okay? Or let's keep it like that. Yeah, like one direction vector that goes toward you, Chavi, and one that goes up like this. Nice and you know, like this, up and toward you. Let's say that my line is diagonal. Well, the two direction vectors that you have here going up and forward can actually be combined to generate a diagonal vector. And that would be parallel to your line. It would be parallel to your line. So let's generalize a little bit, okay? Let's generalize. Let me go back here. So, with this, let's say this is D1, and these are V1 and V2, the direction vectors again of the plane and of the line. So, for infinite or for an intersection that is a line or no intersection, the first check that we have to see is R, or rather is D1 equal to a linear combination of the V1 vector and the V2 vector. If we find that that's true, we're in this scenario. Okay? So we start with this. And then depending on the answer, we move on. So if it's a yes, we have to ask another question, right? Is there a point on the line that doesn't belong on the plane? So we have to answer this for the next. And again, we have two options. So if it's a yes, if there is a point that doesn't belong again on the line but belongs on the plane, we get no intersection. No intersection. But then if there isn't, we get intersection is a line. Is another line. Beautiful. And if you're in this scenario over here, where again, you didn't find that that D1 is a linear combination of the others, you get a point intersection here instantly. And that's how this flowchart goes. It's really useful stuff. I wish they told you this kind of stuff in class. There you go. Very nice way of telling what kind of scenario you have here just by using your logic. I didn't do anything crazy. I just looked at my hands. I brought up a plane and a line and I thought about it, you know? And then I formulated how my thoughts look like in terms of linear algebra terms. I didn't do anything other than that. And I created 3 tests. So that's why I said we don't have time today, because obviously, you see, this is pretty involved. But I can very much bring this up next time, okay? I suspect here that it's going to be a point intersection. Maybe I can squeeze it in the recording if I have it solved. Do I have it solved? I think I do. Okay, so I tried here to find the point of intersection a different way. We definitely have to talk about this a little longer. So I converted everybody to parametric, including the plane. And the plane, to get it in parametric, yeah, it seems like a little bit of a pain. So I'll talk to you about it again. Please bring it up if you want it done next time, okay? Please, I don't want to leave it hanging. But these are the 3 scenarios you could have. Okay, Chavi? All good? Perfect. Alrighty. I was wondering if the chem tutoring mentioned during first session will be willing to tutor. I've messaged them. Hold on, let me cut the recording here because that's irrelevant. One sec.